Hello there. In the last video, we discussed a few theorems associated to the divisibility between two numbers. One of those theorems was this. So we can let a, b, and k all three be integers, and we can let them be positive without loss of generality if we want to. Then the greatest common divisor between a plus kb and b is equal to the greatest common divisor of a and b. We're going to use this theorem in order to prove the Euclidean algorithm, which is a method that can easily be used to generate the greatest common divisor between two numbers a and b. Alright, so before we get started, we're going to just lay down a couple foundational things that we should remember from grade school. So the first example is consider the fraction 21 divided by 4. So we know that 4 divides into 21 5 times with a remainder of 1. And we can rewrite this as simply 5 plus 1/4, which you may remember seeing as 5 1/4 as a mixed number, right? But that's of course equivalent to saying 5 plus 1/4. And this representation is what we're going to be using. So what I'm also going to do is I'm going to multiply both sides of this equation by 4. So once we have that, we have 21 is going to be equal to, so 21 is equal to 5 multiplied by 4 plus 1, right? And we can represent any numbers, 21 and 4, in this representation. Namely, we can find this number 5 and 1 such that this linear combination is true. For example, what if we have the numbers 33 and 7? And we can, of course, assume that this number is the greater of these two numbers, right? So we can assume if this is A and this is B, we can assume that A is greater than or equal to B, right? Because we can always switch them around if we need to. So if I want to rewrite 33 and 7 using a combination using quotients and divisors and remainders, then we can rewrite this as 33 is equal to 7 times something plus the remainder, right? So we know that 7 can go into 33 4 times, and 7 times 4 is going to be 28. That means there's going to be a remainder of 5, right? So this is the linear combination representation of 33 and 7. Alright, so now what we're going to do is we're going to introduce a theorem that takes advantage of the theorem that we started off with and also this main principle. So the theorem goes like this. So let A and B both be integers. Without loss of generality, we're going to assume that A is greater than or equal to B, as we just discussed above. And let us assume it has this linear combination representation. A is equal to Q times B plus R. Here Q is the quotient when A is divided by B, and R is the remainder of that quotient. And of course here we can assume or prove that Q and R are in the set of integers, right? So then the greatest common divisor of A and B, namely the two integers we start with, is actually equal to the greatest common divisor of B and the remainder that is generated from that division, right? Alright, so how can we prove this result using the things that we know? So using the theorem that we started off with, we know that the greatest common divisor of A and B is going to be equal to the greatest common divisor of R plus QB and B, where Q is some integer and R is some integer, right? So we know from the theorem above that this is precisely equal to the greatest common divisor of R and B, and that completes the proof. So that sort of requires that theorem that we sort of started off with by assumption, right? Which was the greatest common divisor of A plus KB and B is just equal to the greatest common divisor of A and B, right? So that gives us this result. And this result is actually really, really powerful, and you'll see why in a moment. Alright, so now we're going to go ahead and go through a proof, or try to prove, the Euclidean algorithm. So let's just give a quick statement of it. So the last non-zero remainder of the Euclidean algorithm on two numbers a and b is precisely the greatest common divisor of A and B. All right, so proof. All right, so without loss of generality, we're going to be letting A be bigger than B, both be integers. Right. Now you may be wondering, well, can I let A be greater than or equal to B? Yeah. So just side note, if A is equal to B, then the greatest common divisor of A and B is equal to A, which is equal to B. So that's a trivial case, so we don't need to consider here. All right, so A is greater than B and let them both be integers. So that means there exist these numbers Q and R such that the following is true. A is going to be equal to Q times B plus R, right? And then we're going to repeat this process over and over again. So we need to start defining sequences of things. So what I'm going to do is I'm going to define A to be equal to R0. I'm going to define B to be equal to R1. And I'm going to define this remainder from this quotient to be R2. And this quotient here, Q, I'm going to define that to be Q1, right? All right, so why do I define A and B as if they are remainders? So let's just take a quick glance at this. So if I have A is equal to Q times B plus R, remember that B is coming from a previous step of the Euclidean algorithm, and A is coming from the parentheses there, right? So there's some Q star, there's some integer alpha over here, and that also forces A coming from a previous step somewhere above, right? So we have R0, R1, and this remainder is R2, which is why we sort of denote that. Well, it motivates one representation for why we want that, right? So therefore, we have this starting sequence. R0 is equal to Q1, R1 plus R2. Now it's very important to see that R2 must be less than, strictly less than R1 in this case. And of course both R1 and R2 should be greater than 0. So keep this in mind. So note here that 0 is less than or equal to R2 and that must be less than R1 with the assumptions that we have here, right? So we're going to continue this iteration. So R1 is going to come down and then we're going to have some quotient Q2. R2 is going to come down, so we have R2, then we're going to have some remainder from that, right? So again, we're going to have that 0 is less than or equal to R3 is less than R2, and then we're going to iterate this process again. So R2 is going to come down, we're going to have another quotient Q3, then R3 is going to come down, we're going to have R3, and then we're going to have a new remainder R4. So again, 0 is going to be less than or equal to R4, and that's going to be less than R3. Right, and the Euclidean algorithm, as we should already be familiar, this is going to continue on. So we need to make a couple observations before we make the next step. So let's focus on these inequalities that we've built on the right-hand side here. So we have 0 is less than or equal to some sequences. So we at least have R4 here. So we have R4 less than R3 less than R2 less than R1 less than or equal to R0, which is equal to A, right? So what can we tell about the sequence RK, right? So therefore, the sequence RK is a decreasing sequence. So it's a decreasing sequence bounded above and below. Bounded above by A and below by 0. And it's also important that all of these remainders, they are integers, right? So since this sequence RK is a subset of the set of, we can assume without less generally positive integers, but I don't need to state that, then that means there are finitely many non-zero terms of RK. Namely, at most A of them, right? So whatever it is, A, I'm going to define 0 to be less than n to be less than or equal to A, and of course this is going to be some natural number, right? So whatever that number is, we're going to define that number to be n, because we know that number exists, it is finite, it is bounded above by A, and definitely has to be greater than 0, because we're assuming that A is strictly greater than B, right? All right, so let's recap our Euclidean algorithm. So if R0 is equal to Q1 R1 plus R2, R1 equals Q2 R2 plus R3. R2 is equal to Q3 R3 plus R4. And then this continues on to Rn minus 2 is equal to Qm minus 1 Rm minus 1 plus Rn, right? And then we have Rm minus 1 is equal to Qn Rn plus 0, right? So Rn is the last non-zero remainder of that sequence. And we know that number n does exist because we have a bounded sequence of integers that is bounded above and bounded below. So we know this n definitely does exist, right? Now this does not prove that this is the greatest common divisor of A and B though, right? So we still need to establish that. But we do know that this sequence does terminate, at least in the non-zero perspective. So let's go and show that this actually is the greatest common divisor of A and B, right? All right, so as we know, the greatest common divisor of A and B from the theorem above and the definitions, so A was defined to be equal to R0 and B was defined to be equal to R1, right? So by the theorem that we presented before this and proved in another video, this is equivalent to the greatest common divisor of R1 and Q1 R1 plus R2, right? So that is, the theorem that we had presented before. Now, what exactly is this? Well, this actually is something else. Do you know what it is? It is precisely R0, of course, right? That is the definition of R0. But according to the theorem, so by previous theorem, this is going to be equal to the greatest common divisor of R1 and the remainder of that linear combination, namely R2, right? All right, so then we're going to have, we're going to reverse. So then we're going to have the greatest common divisor of R2 and R1. And R1 is going to be equal to, that's going to be Q2 R2 plus R3, right? And by that theorem again, this is going to be equal to the greatest common divisor of R2 and R3, right? And then we're going to reverse. So greatest common divisor of R3 and R2. We're going to replace the linear combination of R2 with that representation Q3 R3 plus R4, and then use that theorem continuously. And then once we get down to the bottom, we have the greatest common divisor of Rm minus 1 and Rm, right? And then finally we have the greatest common divisor of Rn and 0. Right, so we have the greatest common divisor of A and B is the greatest common divisor of the last non-zero remainder and 0. So here's a question. What is the greatest common divisor of a non-zero number and 0? Take a minute and think about that question. So divisors of, so let's look at the divisors of Rn. So we know 1 is clearly the divisor of Rn. There might be others, there might be none, but we know that at least Rn is going to be the greatest number that is going to divide into Rn evenly. And the divisors of 0 are, of course, all the non-zero integers. So we have 1, 2, 3, 4, Rn. We know that's greater than 0. Rm plus 1, Rm plus 2, and also any integer above that, right? Because this is, of course, n. So as we know, the greatest common divisor of these two sets is clearly Rn, right? So that means the greatest common divisor of A and B is Rn, right? where Rn is the last non-zero divisor of the Euclidean algorithm, right? And that completes the proof of this Euclidean algorithm, that it does generate the greatest common divisor between two integers a and b. Anyway, I hope you understood each of these little components to this proof, because it definitely is a very powerful theorem and good algorithm for finding greatest common divisors and simplifying fractions and finding prime products of large integers and so on. Hope you enjoyed.